We did pretty well understanding terrestrial worlds, which are relatively similar to Earth. Now we can get ambitious. We can see what we can say about the Jovian planets and see how much of what we've understood translates to these more interesting systems. Looking at their motion in the solar system, the things I'd like to point out is the inclinations of the orbits are very small. The periods of the orbits are interesting. Jupiter and Saturn are locked, as you can see if you do the calculation, into a 2 to 5 resonance. So the 1 to 2 resonance that destabilized things has locked into a stable 2 to 5 resonance, which is anchoring, if in some sense, the stability of the rest of the solar system. In terms of the rotation periods, the spin periods, notice how fast all of these objects spin. The slowest is Uranus with a 17-hour spin. Jupiter, in its entire mass, rotates about its axis every 10 hours. If we think about these giant planets forming out of a gravitational collapse, a gravitational instability, then we remember that this will acquire angular momentum from more distant parts of the cloud. This explains the rather rapid spinning motion and will have consequences as we go along. The other thing to note is that the tilt angles are moderate except for Uranus, which has an axial tilt of 97 degrees, which means its axis essentially is not perpendicular to the ecliptic, but is essentially in the plane of the ecliptic. This gives extraordinarily marked seasonal effects on Uranus, and even from observations from Earth, we'll be able to remark those. Notice that those seasons are rather long, since the year is 84 years long. And so, in some sense, Neptune, with the longest year, was discovered about a year ago. This is what we see in terms of their motions. We talked about how they got there. Looking at the surface or the atmosphere, which in these cases is the same thing, since this atmosphere, primarily hydrogen, molecular hydrogen, and helium, is all we're going to see because there's a sufficiently deep atmosphere on all of these that we cannot see through them. The atmospheres are always hydrogen and helium. Uranus and Neptune acquire their blue tint from traces of methane. What do we see looking at the surface? Well, the surface is the same as the atmosphere because all of these planets have sufficiently thick atmospheres of hydrogen and helium that we cannot see through them with any instrument. And so the atmosphere is what we see. The atmospheres are hydrogen and helium. In the case of Uranus and Neptune, a trace amount of methane tinges them blue. And what we see when we look at this wonderful image of Jupiter is the lines of latitude tracing convection cells. The atmosphere is heated by the core from below, just as on Earth. This, in conjunction with the more rapid rotation, leads to these bands and zones, which are tracing the patterns of the convection cells. Together with the rapid rotation, you get very massive global winds, and at the interfaces between differing directions of global winds, you get intense storms, most famously the giant red spot on Jupiter, a storm the size of Earth, which we conjecture has been ongoing for 100,000 years. But there are many other persistent storms on Jupiter. Comparing this to an image of Saturn, we see similar things. We see the same band structure, although less pronounced. The dark coloring of some of the regions on Jupiter is attributed to the rising of some form of complex, perhaps hydrocarbon molecules, but nobody's precisely sure what causes the coloring, and in particular, nobody can explain why once in a while one of those dark belts disappears for a few months, as happened about 6 months ago, and then reacquires its colors. It's not a change in the global circulation patterns, but something else, and nobody completely understands it. We see the same kind of storm pattern on Saturn. We see similar effects on Uranus, and indeed similar effects on Neptune. On Neptune, what we notice is the hemispherical variations with season. This happens on Uranus. It also happens on Neptune, despite the tilt not being as extreme simply because the seasons are so long that global hemispheric effects take place in the course of the 164-year orbit. Looking inside the planets, well, we don't do seismology on these giant planets. We conjecture the structure of their inside from modeling, as we do for the terrestrial planets, combined with measurements of the oblateness. The rapid spin causes all of these planets, like as indeed the Earth does, to be slightly thicker around the equator than around the poles. This is because of the effect of spin. By measuring how oblate they are compared to how they spin, we can produce some estimates of the internal structure. And the internal structure that seems to obtain for Jupiter and Saturn is that inside the external atmosphere of hydrogen and helium is a mantle made of metallic hydrogen. Hydrogen, if you look at its place in the periodic table, should be a metal. Metallic hydrogen is certainly not found naturally on Earth. It occurs only under very, very high pressures. It was only produced on Earth in, I think, the 80s. But it exists naturally under the extreme compression of the immense gravity and the immense weight of the heavy atmospheres of these planets. We have the usual hydrodynamic equilibrium where pressures in the cores of these planets are very, very extreme and decrease as you move out. But since the atmosphere is thousands of kilometers thick and very heavy, even at the bottom of the atmosphere, pressures are intense. Metallic hydrogen is a conductor. The rapid rotation leads to a strong dipolar magnetic field for all of these planets. In the case of the gas giants Jupiter and Saturn, this magnet is aligned very nicely with the planet's rotation axis. In the case of Uranus and Neptune, the mantle is actually compressed ices, so water, ammonia, methane, etc., at high density. These two can conduct, but the mechanism is a little bit different. The understanding is incomplete, but one of the manifestations of the difference in the mantle is that the magnetic fields of Uranus and Neptune are 60 degrees tilted relative to their direction of rotation. Inside each of these is a core, presumably the seed that started the planet's growth. As you can see in this image, the core is roughly Earth-like in size, probably more massive because compressed, and has an iron-rich inside and perhaps a silicate outside if it chemically differentiated. So the core of each of these planets is about the size of Earth itself. Again, the interiors of these planets are both extremely compressed and very, very hot. In the case of these planets, much of the internal heat, remember, only the core is rich in heavy elements. Here, this is a tiny fraction of the actual huge planet. And so radioactivity does not play a large role in maintaining and producing internal heat. Internal heat is produced by Kelvin-Helmholtz processes, by precipitation, and by increased and continuing compression of the interiors of the planets. In the case of Saturn, precipitation of liquid helium. So liquid helium rain at high pressure is the mechanism by which Saturn is chemically differentiating. And this is significant if you do the calculation of surface temperature based on our black body calculation compared to the measured temperature of the surfaces of these planets. You'll discover that both Jupiter and Saturn radiate about twice as much energy as they absorb from the sun. This is the difference is being made up by continual heating from the core through mostly Kelvin-Helmholtz processes. And we have this strong magnetic field. This is an aurora on Jupiter's north pole. These are aurorae on Saturn's poles. And if we look for aurorae on Uranus, you can see that if you look at the ring structure that indicates the equator of the planet, this is not at the pole. The pole is way over here to the left. And the aurorae are showing up at intermediate latitudes. This is indicating to you the offset of the magnetic field. Indeed, this reminds us that the most impressive structures carried by these giant planets are their rings. And we understand, in some sense, where these might come from. These planets are formed by a gravitational instability in the nebula, collapse, and the collapse will be a accompanied by a flattening into an accretion disk from which the planet acquires gas and dust. Near some of this leftovers of the nebula will form moons. So most of these planets have moons that orbit them in their equatorial plane. These moons formed within the accretion disk, just as the planets formed in the sun's accretion disk. But close to the planet, tidal forces can prevent gravitational accretion. This would have been true in the case of the sun as well, except that close to the sun, whatever didn't accrete into Mercury was blown away by T-Tauri winds. Planets do not generate T-Tauri winds, so whatever accreted near the planet, too close to form a moon, will produce ring-like structures, and we have ring structures around Jupiter, and ring structures around Uranus, and Neptune, and ring structures around Uranus, and the beautiful, magnificent rings around Saturn. For reasons nobody completely understands, the rings around all of the three giants other than Saturn are dusty and dim, whereas Saturn's rings are almost 99.9% water ice. Water ice, as we know, is brilliant and shiny, which is why the rings appear so bright. We see here that the rings are discrete. The large gap here, the Cassini gap, is visible in a moderate telescope from Earth. The slightly smaller gap farther out, the Encke gap, is visible with a more advanced telescope. But upon closer inspection, it turns out that these rings have a very, very fine internal structure. We'll get into that in a second. Let's understand what it is that I'm saying when I say that too close to a planet a moon cannot form. The limiting distance, the closest distance at which it can form, is called the Roche limit. It was computed in 1848 by Roche. And the idea is this. We have a planet over here. We're trying to form a moon over there. We will say a moon can accrete and form, provided that the tidal forces of the planet are not enough to blow it apart. So we've done enough to do this calculation that Roche did. We give this a mass m planet, give this a mass m moon, set them a distance d apart, and the question is basically, this moon is held together by gravity. Is the moon's gravity enough to hold it together against the tidal forces? If we drop a pebble on the surface of the moon, will it be lifted by tidal forces or not? And so we know how to do this. We need to compare the tidal acceleration due to the planet's tidal forces on the moon. We computed this in the past. It's 2 times g times the mass of the planet times the radius of the moon divided by the distance cubed. This is the tidal acceleration with which the planet tries to stretch the moon as we have it here in the horizontal direction. And we need to compare this to the gravitational acceleration due to the moon's own mass at its surface. And this, of course, is g times the mass of the moon divided by the radius of the moon squared. As d gets smaller, the tidal acceleration increases. When it overwhelms the moon's own gravity, the moon will simply fall apart as long as it's gravitationally bound. Or if we're trying to form a moon by gravitationally binding moonetesimals, the moon will never form and will end up, as we'll see, with ring structures. So let's write these two and set them together. This is setting the gravitational acceleration on the moon's surface equal to the tidal force generated by the nearby planet, dividing through by r and canceling the g's as usual. I'm going to put this down over here, and I find that I have this interesting expression that says the mass of the moon divided by its radius cubed is equal to twice the mass of the planet divided by the distance cubed, which it's interesting to write in a different way. You write the mass of the planet divided by the distance cubed, but then you divide and multiply by the radius of the planet cubed. Now, why is this a useful way to write it? Because the cube of the radius is a measure of volume. Remember that the volume of a ball is 4 pi over 3 r cubed, and that if I know the average density of an object, then its mass is the density times the volume. So dividing the mass by r cubed up to irrelevant canceling factors of 4 pi over 3 gives me a measure of the density. In other words, what this equation tells me is that the density of the moon is twice the density of the planet, times the ratio between the cube of the ratio between the radius of the planet and the distance between them when that distance is at the Roche limit, when tidal forces are just enough to rip the planet apart. In other words, I can now solve for D in terms of the densities and the solution that I get. So here's the expression written that way. Again, I rewrite things in terms of the densities, and this says that the density of the moon is twice the density of the planet times the radius of the planet divided by D cubed. Now multiplying through by D cubed, dividing by rho m, I finally find, and then taking a cube root to get my answer, I find the fearsome equation on our splash page that says that the Roche limit, the closest distance at which a moon can survive, that's D, the Roche distance, is given by the radius of the planet times the 1/3 power of the ratio of twice the planet's density to the moon's density. To make a reasonable calculation, let's assume, for example, that we're describing Earth and Earth's moon. What is the nearest distance to Earth that our moon could possibly have formed? Remember, it formed much nearer. Well, let's give the moon half of Earth's density, so twice the Earth density divided by the moon's density would be about 4. 4 to the 1/3 is about 1/6. So in the case of a planet twice as dense as its moon, you find that the minimum distance is about 1.6 times the radius of the planet if rho planet is twice rho moon, which is the case for our moon. And so our moon could not have formed less than about 2 Earth radii from the center. In other words, about 7,000 kilometers away from the Earth's surface. Nearer than that, our moon would have been ripped apart by Earth's tidal forces. And this is a very useful expression. Objects inside the Roche radius cannot possibly be gravitationally bound. Now, that does not mean that they are completely ground to dust. At some point in the solar system, the rough scale is about 1 kilometer. We will do a homework problem that will help us understand how that happens. At some small scale, remember the planetesimals were held together chemically. Smaller things are held together by chemical forces. They, at small distances, are able to withstand gravitational tidal forces, but gravitationally bound objects will be dispersed over time. And so the way that this will work is if you bring a moon to within the Roche radius, which is indicated by this white ring, tidal forces will elongate it, and when it crosses the Roche radius, it'll start to fall apart. Remember, it's being extended, so parts near to the planet will fall towards the planet, parts far from the planet will fall away from the planet, and because they're all moving, imagine this thing was in orbit, all of the moon was moving with the same orbital velocity. The bits that have fallen too close to the planet are now moving at a speed too small for their now lower orbit, so they will fall into elliptical orbits with this as their aphelion, and the bits that are falling away from the planet will be moving too slow, so they will fall into elliptical orbits, and when everything settles down into circular orbits, the guys that fell towards the planet will have advanced ahead. The guys that fell into away from the planet will have been left behind, and basically the whole structure is smeared out along a ring. We'll see this happening again and again. When tidal forces rip something apart, they generate, that is in orbit, they generate a ring structure. So this is where the rings could have come from, or why the rings formed but no moons. But stability over the long term of such a ring structure, you'd expect collisions between ring particles, you'd expect admixture. Looking at Saturn's rings, we see that there are changes in composition between thousands and thousands of ringlets. It's not completely understood what maintains the stability of this amazing structure. For the record, Saturn's rings are about 150,000 kilometers in width, but by some measures only 400 meters in thickness. This is an extremely thin object, precisely on the equatorial plane, and made up of essentially chunks of water ice, but with various additives or various trace amounts of other materials so that they have slightly different properties in the various ringlets. And One of the things that helps maintain this structure is the existence of moons that orbit both within the ring system and outside it. They produce these gaps. These gaps that are marked here are gaps at which objects orbiting in the ring would be in resonant orbits with the moon. Just as in the asteroid belt, this would cause them to be moved into eccentric orbits and eventually ejected. So nothing orbits in the gaps, and this separates ringlets from each other. Moreover, there are moons that orbit inside the rings, inside the Roche limit, where a moon cannot exist. Indeed, those moons are slowly being ripped apart and perhaps resupplying material to the rings as the material is being lost to collisions. And these objects are both very beautiful and very intriguing, and I don't think we completely understand what maintains their structure, but they're certainly a generic property of accretion systems.